In this video, we're going to look at an exam question that involves working with a PDF, a probability density function, as well as a CDF. So we're given the question and we're given a probability density function ft, but this has an unknown constant c. Now the key result with PDFs is that because they're a measure of probability and total probability is always equal to 1, that means that the interval between minus infinite and positive infinite of our PDF ft is always equal to 1. So we're going to use this formula in order to find out what c is. Well, in this example, our ft is sort of slightly complicated. There's sort of split into different regions. There's a region less than 0 where the ft is 0. There's a region between 0 and 9 where we have a c 81 minus t squared, and there's a region greater than 9. So we can split this integral into an integral between minus infinite and 0 where ft is equal to 0, and we also have an integral between 0 and 9 where ft is equal to c 81 minus t squared, and a final integral between 9 and positive infinite where again our ft is just equal to 0. That's because of this 0 otherwise part. Now obviously the integral of 0 is just 0, is just going to give us 0. So we can ignore those, and all we end up with is this integral between 9 and 0 of c 81 minus t squared. Well, that's the same as c, and then that's a constant which we can pull outside. Then we get 81t minus t cubed over 3 when we integrate. And if we evaluate that between 9 and 0, we get c 81 times 9 minus 9 cubed over 3. And then the 0 bits, the lower bound 0 will just get as 0 in our integral. So actually calculating that, I think we get 486c. And remember, this whole thing was equal to 1. So c is equal to 1 over 486, which is the required result. Okay, let's look at part B then. Part B tells us to look at the CDF. Now, the CDF is sort of a cumulative probability. So the CDF, denoted by capital F, is given by the integral between minus infinite and infinite of, between minus infinite and t of fx dx. So x is just a dummy variable, it doesn't really matter. And this tells us the probability, the total probability to the left of small t. So it tells the probability that my random variable, capital T, is less than or equal to small t. That's what the CDF is. Okay, now the tricky bit again is because we have some different ranges. Well, let's look at our PDF. Our PDF, sorry, that's not a very straight line. Our PDF looks like this. It's 0 when t is less than 0. So we've got this region here where it's 0. Between 0 and 9 is equal to 81 minus t squared over 486. So it looks like this. It starts there and it comes down to there, because when in this case, although not always, when t is 9, this ft becomes 0, and then when it's t is greater than 9, again, actually this is this bit. So this is our PDF graph. Now, clearly, sort of in this area, because the probability is 0, there's no probability accumulation. In that area, and similarly, because the PDF is 0 here, there's no probability accumulation here. And all of the prob accumulation is in this bit where it's positive. Well, what does that mean? Well, that means that, well, if small t is less than 0, the probability that t is less than or equal to that small t is obviously 0. There's no chance that we have we can't, which is ft is 0. Below that, there's no probability accumulation down there. And similarly, if t is greater than 9, well, the probability that t is less than or equal to this small t has to be 1, because all possible values of small t are all possible values of my random variable t are less than 9. So the probability that the random variable capital T is less than this t, which is a number bigger than 9, has to be 1. It's certain. So we know the CDF in these two ranges. So the only other range we have to look at is the range 0 is less than or equal to t is less than or equal to 9. Well, then pt is less than or equal to t equals ft is just the integral between minus infinite and t of fx dx. And that is equal to, well, it's equal to the integral between minus infinite and 0 of fx dx. Well, that we already know is just 0, because there's no probability accumulation there, plus the integral between 0 and t of fx dx. Well, between 0 and t, from the first part, I'll just move it over here, this is the integral between 0 and t of, well, we worked this out in the first part, it was, well, I didn't say we worked it out, we already had this value, it's c81 minus t squared. So the we run ft, we actually now want to put an fx. This is c, so that's 1 over 486. And it was 81 minus, rather than t squared, we use x squared, because we're integrating with respect to x, which is just a dummy variable now. And if we do this, we get 1 over 486, 81 x minus x cubed over 3 between 0 and t. Now the 0 lower bound gives this whole thing into 0, and the t upper bound means we replace the x with t's. We get 1 over 486, 81t minus t cubed over 3. Okay, and we're sort of done now. We have to just write down the full ft. Well, we had the three regions. We had ft is 0 for t is less than 0. We had ft is 1 for t is greater than 9, and for t is between 0 and 9, we get 81t over 486, and that's just t over 6, and then minus t cubed over 486 times 3, which is 1458. So that is my CDF with the three regions. And again, if we just go back to the question, hopefully, yeah, that lines up with the answer that they've given. So finally, we're just going to look at this final part, the probability that the customer queues for longer than 3 minutes. So this is part C. Well, this is the probability that t is greater than 3. Well, that's the probability that's 1 minus the probability that t is less than or equal to 3, which is 1 minus f3. Well, because 3 is between 0 and 9, this is 1 minus 3 over 6 minus 3 cubed over 1458. And you just plug these numbers into your calculator, and I think this comes out as a exact answer as 14 over 27. That's the probability a customer chews for longer than 3 minutes.